Okay, right, what I'm going to do in this video is show you a number of things, one of which is firstly the scripted version of the 3-span beam file of the example that we went through in class. So I'll just double click on this 3-span beam.lgw file where I've just edited this in Notepad and I've just put a load of commands down to ensure that you know, these get read in sequence and then the model is automatically created. Now look, wherever you see an exclamation mark, that means that command won't be read in by ANSYS. It's purely for me to put some description in the file so that I know what each command is doing. So look, the first thing that's issued is a finish command, just to make sure you're back in what we call the routine begin level. And then the next command it takes in is the title, 3-span beam. /prep7, enter the preprocessor. Then define the element types. Element type 1, beam 3, okay, it's just a 2D beam element we're using. Next, define the real constant properties. That's all what we need to be set up for each of the spans, the height, the area, second moment of area, that kind of thing. Then we come to the material properties with the MP command, which is essentially your Young's modulus and Poisson's ratio. Now, just dragging that up there, create the first node, copy it along 25 times. That's all we're doing there. Set the attributes for the first span, generate the first element, copy it. Change the real constant to the second span, generate an element, copy it. Let's just drag it up again. So for the third span, change the real constant set to 3, generate an element, copy it 8 times. That should have created the model nodes and elements, and then you say finish, because that gets you back to the routine begin level so that you can enter the solution phase. Set the analysis type to static. I think we've already done that somewhere else perhaps, but anyway, that's the default, so you may not need to enter that command. The next bit then is to apply all the displacements. Now you want all the UYs held at 0, and plus at the end nodes you want all the degrees of freedom because they're fixed ends. So that makes sense. I've done that for each node there that is representing a boundary. Okay. Next bit, I want to apply pressure to the spans. So what you have to do here in the scripting sense is just to select all the elements in the first span, so 1 to 8. Apply the pressure of 15 kilonewtons per metre on there, or 15,000 onto the beam. Then once I've done that, go back and select all of them again. To apply pressure to span 2, just select the elements associated with span 2, put your 30 kilonewtons per metre on there, go back and select them all again. And then for the force, we're just applying that to a node, so you just use the F command to apply 60 kilonewtons. Don't forget it's minus because it's acting downwards. Define analysis type static, that's already there. I think we should have got rid of that one, but never mind. It's just that's just a redundant command again. Start the analysis, so solve it. Hopefully that will be okay, no problems there. Then finish, go back out of the solution phase and enter the post processor. Let me bring that up. Set 1, 1, so first load step, just bring that in other words, bring the results in from the database. Then plot the displacement. Now what I've done there is, because you'll see the displacement on the menu, or sorry, on the graph when I run it through, but if I carried on the commands it would just flick up on the screen and you wouldn't see it. So what I've done is I've issued the /wait command for 10 seconds there, which allows the viewer to see it for a while before the commands then re-execute. This sets the E-table commands to drag out the miscellaneous items 6 and 12, which we know are the moments, and this PLLS, plot line stresses, plots moment I and moment J with a scale factor of -1, so we get the bending moment diagram acting the right way. Okay, so I'm just going to minimise that. Go to ANSYS. There we are. So if I go File, Read Input From, and I go 3-span beam.lgw and then click on OK. Solution done. You can see how quick it is. So this is going to wait 10 seconds now with that on the screen. Wait for it. There we go. Bending moment diagram. So all of that is done automatically. Now, let's just go back to that script file if it's going to come up. Let's just minimize that there. Come up here. You see the way this works, if I want all of these commands to know what these commands do, I go to ANSYS help, type in that command, and then it gives me the sequence that follows. So if I want to know about the element type, I just type in ET, comma, ET, then have a look on the help file, and it tells you what follows in sequence in terms of the comma delimited numbers or items that follow. Okay? Again, like the real constants, if you type in the R command, it'll tell you what sequence of R commands you should use. That tends to be element specific, so you'd need to look at the element as well. So all of these commands as well could be parameterized. I'll try and do that in a separate video where I actually program this. This isn't programmed, this is just a script file. But essentially, when I've got input, I can have an input to say, tell you what, I'll have the length of the beam, and then a little bit later on down here, that length of the beam, I might have called it L. L can be one of the parameters that goes in instead of a number here. If, for example, if I want to change Young's modulus, I could say, have a variable called mod, ask the user to put that in, that then takes it, and I could have, instead of where I've got 2e to the 10, I could have mod, and then that would obviously take in that parameter. But I think I need to explain that more thoroughly in another video. Okay, so the other thing I want to look at now is to add gravity to this model. Okay, so let's just have a look. We can see minimum moments, maximum moments, 28 there, 37 kilonewton meters. So what I'm going to do, I'm going to add 100 kilos per meter to each of these spans, see what happens to the bending moment diagram, and then what I'm going to do is just show you what sort of forces I might try and extract if I want to, say, design a connection, let's say about node 17. Alright, anyway, before we do that, we're going to preprocessor, real constants, add, edit, delete. Now I've got to go in to each of these real constants, so they are for beam 3 there. What I'm going to do, added mass there, I'm going to put 100, so it's 100 kilos per unit length, so my units are meters, so it's 100 kilos per meter. So let's think about it logically. 100 kilos is about a kilonewton, so that means we're adding about an extra 4 kilonewtons on these spans. Alright, let's click on OK. Now I need to edit that for all of these real constants, so just bear with me while I do that. 100, click on OK. For set 3, edit. Okay, did mass 100. Okay, click on OK. Right, hopefully that's all done. Just as a quick check, I'm going to list properties, all real constants. Yeah, you can see there's all my real constants. At the end there, 100, 100, 100. So I'm OK. Now I want to apply gravity. So I go into the solution phase and I go define loads, apply structural inertia, and you can look down there, gravity. I want a global gravity, so click on global, and all it's asking is for an acceleration, because if you think about it, force is equal to mass times acceleration. We've got a mass, we need to tell it what the acceleration is, and that is 9.81 in the y vertical direction. Look, I can put all sorts of accelerations in different directions, so I would apply things like wind, maybe, which might act on well, I know it's more like a pressure, but you may have other inertia effects. So certainly for earthquakes, it would be quite important. Anyway, why is it positive? That's because the boundary conditions accelerate upwards towards the model, not away from it. So they are going in the vertical positive direction. So click on OK. I'm now going to solve current LS, click on OK, job done. Nice and quick. Okay, so let's go and have a look at general post-processor, read results, first set. So hopefully that's read in results of the database for me to look at. So I'll go plot results, deform shape, deform plus undeformed. pretty similar, but you know, we haven't put massive amount of extra self-weight load on there compared to the loads that were before, so I wouldn't expect a massive difference, but it should be a little bit. Now, contour plots. So I want to plot that bending moment diagram. Before I do, I've got to go back into the element table and update it. So element table, define table, because look, I've got them already there. That's great, but they've still got in the table the previous analysis's data. So I've got to click on update and it becomes current. Close. Okay. So now what I do is I go up to plot results, contour plot, line element results, mom I, mom j, -1 on the underformed shape. So hopefully there is my bending moment diagram now. Now you can't really discern, there will be a slight curve on this one here because you've got a point load and you've got a UDL, but the UDL is so small compared to the point load that piecewise linear form still dominates. Okay. Anyway, what I want to do is around about this joint here, which is I know is node 17, I want to look at the forces that I might extract if I want to design a connection here. So if I had a moment connection, it's going to have moment and shear on it, isn't it? So if I now go list results, element solution, and I go to structural forces, let's go to all available force items so we can see what's going on. Now we can see here the element number up here, FX direction, look, there's nothing going along in the axial direction, so that's fine. But these FYs are essentially vertical forces across a section, so they are your shearing forces, aren't they? Okay. So if you look, say we want, let's look at element 16, and I'm going to look at node 17 because that's where the support is. There's a joint. So if I was looking on span 2 to look at the connection there, you can see I've got a shear of about 65-ish kilonewtons, and my moment is just over 39 kilonewton meters. So I'd have to design my connection on that side for span 2 to take those forces on moments. Let's look at the other side on span 3. You can see element 17 there. Fy minus 35, about 35 kilonewtons there. So I'll be designing my shear for about 35 kilonewtons. And here, again, the moment is equal and opposite on that side of the moment connection. So I've got to take the same moment, but a different shear on that side. Okay? Anyway, that's the end of this little ditty. Hopefully that's given you a bit more food for thought. As I say, the script file is included on Blackboard, so you should be able to have a play with that. But in the fullness of time, in a week or two's time, what I might do is get a script file which I've programmed so that those of you who are keen to take that, let's call it the more professional side or the professional way to use ANSYS, you can take it further that way. I might also include some other videos on some strange and special objects showing you how to perhaps do or create some models using direct generation techniques. Anyway, that's that for the moment. Let's just finish now. Bye.